In this example, we're going to come up with an equation to represent the scenario here. Zoe's swinging on a swing at a constant motion. At t equals 1 second, she is the farthest back that she can go, which is 2.5 meters from the vertical position that the swing is in when it is at rest. So it's 2.5 meters back from the resting spot. And at 2 seconds, she is the farthest forward that she can get from that rest position. What is the period of the function and what does it represent in this situation? Use the information to find the value of k for the equation. So our goal eventually is to get the k value. So think of it this way. The swing normally hanging straight down, that's the rest position. When she swings as far back as possible, she's 2.5 meters from her rest position, and that is at time of 1 second. And then at 2 seconds, she is now as far forward as she can get, which would also be 2.5 meters from the rest position. So that took a total of 1 full second to go from the farthest back to the farthest forward. To complete the cycle, she would have to get back to the back position again. So a total then of 2 seconds, 1 second to go from back to front, and then from front back to back again would be 2 seconds. So the period is 2 seconds. It represents the length of time it takes for one full swinging motion. So hopefully that makes sense, because then the process starts again and then we would have the next cycle. So to get our k value, we know that k is just going to equal 360 divided by the period. So we have to take k to be equal to 360 divided by the period, which is 2 in this case. So our k value for our equation is actually 180. Okay, and our x for our equation, our independent variable, is going to be time, because this is based on time. What is the amplitude of the function and what does it represent in this situation? So basically we're looking at that rest position and how far to the left and how far to the right we end up going. So looking at our rest position here, we're going 2.5 meters to the left, come back to rest position, and then we go 2.5 meters to the right, come back to the middle or rest position. So that middle spot is your axis of the curve. The amplitude is 2.5 meters. So 2.5 meters, and it represents how far to the left or how far to the right or how far back and how far forward from the rest position Zoe ends up going. Now, as I've mentioned already, the equation for the axis of the curve is that middle point, which is the rest position. In this particular case, I would make that just equal to 0 because you're going to the left by 2.5, so that could be a negative 2.5. And then we're going to the right 2.5, or forward positive 2.5 from that 0 position there. So our axis of the curve represents the distance from the rest position, which actually is the rest position itself. All right, we need to sketch a graph of Zoe's distance from the vertical resting position compared to the time on the swing. So I've got my horizontal axis being the t for the time that she spends on the swing. I have my vertical axis labeled as d to represent the distance or displacement, either forward or back from the horizontal or the vertical position, that resting position there. Now we know that from the question, at 1 second, she is the farthest back she can possibly be. So she's backwards, so I'm going to make that my negative value. So at 1 second, time of 1 second, she is as far back as she can go at 2.5, or think of that to the left by 2.5 meters or to the back 2.5 meters. I know that at 2 seconds, she's the farthest forward she can possibly be. So at 2 seconds, she is going to be at positive 2.5. So this is my positive 2.5 up here. And that means halfway in between, she should be hitting the rest position, that vertical straight down position. So that would be half of our cycle. Then that means that at 3 seconds, she should be back at the farthest back she can possibly go again, or at 1 second before her, so at time equaling 0, she should also have been at her maximum position there. Okay, so I've developed my nice little sketch from this, and from here we can use that to help us gather information for our equation. And that's part E, right? The equation to represent Zoe's distance from the vertical resting position of the swing. So now with this graph, I can see that it would make sense to use the cosine curve because on the y-axis, I'm at the maximum position. If I use cosine, then I don't have to worry about any phase shift on this equation. I also am at the max, so I don't need to make it negative cosine. If I was on the y-axis and I was at the minimum, then I would want to make it that negative cosine value. All right, our amplitude we got to be 2.5, so amplitude goes first. I said cosine was probably our easiest choice, and let's make it easy if we can. Our k value we got in part A, the k value was 180. I'm going to use t for time. I'm going to go back and change that, the y. And then the axis of the curve is +0, so I don't need to add anything onto the end. And I'm just going to change, instead of a y, I'm going to make that a d for displacement, how much left and right she is, or forward and back. And with an equation, when we create an equation, we should have let statements or information defining what each of those variables represent, as well as the units that represent the units of measurement for each one of those variables. So I'm going to say where d is the distance, or d is the distance left or right of the resting position in meters, or forwards or backwards, whichever way you're looking at it. I kind of looked at left and right based on the side view that I drew up in the picture of the resting position, and t is the time in seconds. Okay, so you should always define your variables when you create equations like this, so that everybody is clear about what they represent and the units that go with them. Okay, this example is talking about a Ferris wheel. It has a radius of 4 meters. The axle of the wheel is 5 meters above the ground. It takes 40 seconds for the wheel to make one rotation. A passenger named Ernie is at the height of the axle and heading upwards when tracking begins. Write an equation to represent Ernie's height compared to the time that he has been on the ride. Okay, so I would suggest making a little sketch of this situation and see if you can come up with the things like where the axis of the curve will be, like what the amplitude will be, like what the period is going to be, which then means we can get the k value for the equation. And then, of course, any phase shift value we might need for this. So take some time and do that. Put the video on pause and then come back and see if you agree with me. Okay, looking at this, I'm going to create my equation, or my graph, I should say, to start with. I know that Ernie at time 0 is at par with the axle, and the axle is 5 meters above the ground. So that's going to be my axis of the curve, because from there he heads up a radius of 4 meters, so he's going to be 4 meters higher than that, which takes him up to 9 meters. So our amplitude is 4. And then we reach a low point of 1, because 4 meters down from 5 would be 1. And all of that is taking a 40-second time frame here. So based on what I have here, I know my amplitude is 4. The axis of the curve is 5. If I work with sine, I don't have to worry about a phase shift because I'm on the axis of the curve on the y-axis, and I just need a k value. A k will be 360 divided by the period, and the period was 40 because it took 40 seconds to create one cycle, and that gives us a k value of 9. So I'm just going to use the sine curve. Y equals, I'm not going to use y. I'm going to use h for height. So I'm going to h, the height, based on time t in seconds, is given by the equation 4 for our amplitude, sine 9 is our k value to create the period of 40. I'm going to put t for time. I don't need a phase shift, and I'm going to put +5 because that's the axle of the wheel. That's the middle point, the halfway between the maximum overall that Ernie reaches in height and the minimum overall that Ernie reaches in height. And then I'm going to define my variables here. Okay, where h is Ernie's height in meters above the ground and t is the time in seconds since being tracked. All right, a passenger on the same Ferris wheel named Bert this time is at the lowest point when the ride begins. So Ernie is on a different cart than what Bert is on. Bert is down at the bottom when tracking begins, so he's down at the low point of 1 meter, and then he heads up, reaches the maximum, and comes back down. Now it still takes 40 seconds, so my K value is not going to be any different. My axis of the curve, the middle point, will still be at 5. The maximum value will still be up here at 9. This means our amplitude has not changed. The amplitude is still 4. Our K is still 9. What else do we need? The axis of the curve is still y equals 5. So our curve this time, though, it starts at the minimum. I'm going to use cos, but put the reflection on it. So our h at t is going to equal 4 with a cos 9 still. And I'm going to put a t with that and a plus 5, but I want that to start at the minimum, so instead of just having a 4 there, I'm going to make sure I have negative 4. With that amplitude to indicate it's starting at the low point instead of the high point. It's the opposite. And my overall definition of my variables are going to be the same. So I'll just repeat what I wrote up on Ernie's. Okay, so same definition for the variables, except Ernie is now Bert.